My name is Kayla Smith. I am a graduating senior at Central State, and I'm doing this work on a project that we recently submitted. It is entitled The Impact of Novel H2O Cross-Sections on the Present-Day Martian Atmosphere. So I'm going to take you from the moon to Mars really quick. Okay, so here's a little roadmap about what we're going to go through in this presentation. We're going to put everything into perspective. Then I'm going to explain the model/methods, and then I'm actually going to explain the project, and then I'm going to end with my thank you and acknowledgements. Okay, so Earth then and now. So Mars has always been my first love just because it is my first planet I've ever really studied. And once I started to study Mars and when we started to understand the evolution of the atmosphere, I wanted to understand how that kind of coupled with Earth, right? And so 4.5 billion years ago, our beautiful Earth was a big ball of molten lava. So these beautiful lions could not exist on Earth 4.5 billion years ago. 2.3 billion years ago, Earth was a big ball of ice. So these really cute koalas were unable to exist on Earth 2.3 billion years ago. But at present day, the atmosphere has changed drastically to house life. So I'm able to hang out with my friends and hang out with my parents, and humans are able to exist, and life is able to exist on Earth, and we're all doing great. So that kind of evolution of Earth really inspired me to want to understand the evolution of Mars in greater scale. And so it is argued that Mars once had a very warm, wet, thick, dense atmosphere, about half a bar. At present day, Mars is very cold, thin, and dry, and has an atmosphere of about 6 millibars. So the atmosphere is really, really, really thin and really, really cold. And then if you can see on the plot here on the right here, it's kind of just showing how the water on Earth actually got smaller and smaller and smaller as millions of years went on. And so my project is trying to understand where the water go on Mars. We know a lot of it sunk into the ground, which we can find in the solar ice caps and the carbon dioxide solar ice caps we can find in the surface of Mars. But a lot of it, we want to understand how much of that water actually escaped to space, and essentially how much of the hydrogen actually escaped to space. So to answer these questions, we used the 1D photochemical and transport model entitled KINETICS. It was developed by Caltech and JPL. And essentially, KINETICS analyzes species behavior, atmospheric species behavior in a vertical direction. So we can look at photolysis of species. So for example, if I take a water molecule, I hit it with a molecule from the sun, and it breaks apart into H and OH. And then those species can go on to react with other species and create other molecules. So photolysis is really huge in our model. We can look at thermochemical reactions, ground sinks such as deposition and rainout, atmospheric escape to space, and then upward ground fluxes such as volcanic emission, biology, and things of that nature. And so the model is a 1D photochemical model, so we can only see things vertically, but I will bring in the 2D photochemical model talk here in just a second. So to understand how this H2 is actually formed, we look at the Hock cycle. The Hock cycle is kickstarted by, again, that water photolysis. So this water here will break apart by a photon. It'll break apart into H and OH. And then those species will go on to react with other species and create other molecules. A lot of that OH actually does sink into the ground and contribute to a lot of hydrodeclays that we find on the Martian surface, which Perseverance and Curiosity and other rovers have actually found. But eventually, at the end of this Hock cycle, we will have formed H2. That H2 is light enough to diffuse upwards and eventually escape to the exobase of the atmosphere. So we want to understand how much of the H2 is actually being escaped to space and what photochemical reactions actually contribute to that escape to space of hydrogen. So essentially, this project is wanting to understand if we add more water photolysis into our model, will that actually impact the near surface chemistry and eventual escape to space of H2 in the long run? And so water photolysis at longer wavelengths. So this is kind of what I was hinting at. So previous models and previous studies, specifically Ranjan et al. 2020, actually suggest that water photolysis is non-negligible at much longer wavelengths than previously suggested by previous models. So for example, KINETICS typically drops off about 1950 angstroms of water photolysis. And so we're wondering, okay, if that's it, then we won't see a lot of H2 escaping to space with our model. But Ranjan et al. 2020 actually suggests and actually prove that the water photolysis at much longer wavelengths, extending even so more into 2300 angstroms, actually does exist. And so this tail region here is very, very, very important because we know that water photolysis is non-negligible at those much longer wavelengths than previously found in other 1D photochemical models like KINETICS. Okay, so here is the ratio of mixing ratios. So essentially, we took the new water cross sections provided by Ranjan 2020, the extended water cross sections, more into those greater than 1950 angstroms, and we plotted that over top of the old water cross sections that cap off at 1950 angstroms or KINETICS water cross sections. And essentially, wanted to understand how that impacted the near surface chemistry of Mars over geologic time. And so we see a really big spike in OH, which that makes sense because there's more water photolysis happening. But we also see a really big change in CO and HNO3, so carbon monoxide and nitric acid. So we want to understand how those actually change from previous studies. And so we actually found that CO decreases roughly 20% and 12%. We use two different inputs, so that's why we have two different values there, but it essentially does decrease over time. And that is due to the amount of OH around. So again, with that water photolysis happening and that water photolysis creating OH, there's more OH for CO to attack, which can cycle back into CO2, and that CO will not build up in the atmosphere. On the other hand, nitric acid increases roughly 50%, 18% respectively. And again, that is due to the amount of OH around for the NO2 to attack in the third body radical, and that can form nitric acid, and that can create more nitric acid in the atmosphere. So again, the water photolysis actually does impact near surface chemistry, and our results specifically carbon monoxide and nitric acid. Okay, so here are the CO color maps. These maps are the normal mixing ratio, so it's divided by latitude 0. And then we also have 15 altitude bins, latitude bins that were interpolated onto our altitude grid. So essentially, we took into account the 2D water and ice data provided by EMARS, which is the Gray Bush et al. 2019. And we kind of added in those latitude bins onto our altitude grid to kind of get a more latitudinal perspective of where these species are actually peaking in the atmosphere. So on the left here, it's just straight up kinetics. And we saw that CO was actually not converging to steady state. It was kind of just blowing up in the atmosphere and wasn't really converging. So once we added in that extended water cross sections, again, there's more OH for that CO to attack and kind of cycle back into CO2. And we added in the latitude dependencies for the 2D photochemical model, photochemical data set. We've ended up finding this beautiful CO map here. And so it actually does give a really more realistic picture of where that CO is actually peaking in the atmosphere. So this is just one of the more dramatic examples. We actually did this for a multitude of species. We did this for water, O3, HO2, OH, O2, O, and HNO3 and NO. And so as you can see, the latitude bins actually gave us some more realistic input about where this is actually peaking in the atmosphere. And so, yeah, that's why we added in the 2D photochemical data set to kind of understand the well-roundedness of where these species are actually peaking in the atmosphere. Okay, so the dust storm analysis. So I wanted to understand how dust storms were actually impacting near surface chemistry and especially the hydrogen escape into the atmosphere on Mars. And so we looked at Chaffin et al. 2017. We took his data and again interpolated that onto our altitude grid. And essentially, this is the fractional change of mixing ratio over geologic time. So the X is in seconds and the Y is in mixing ratio, or the ratio of the mixing ratio again. We took the new cross sections divided by the old cross sections again. And essentially, we know that atomic hydrogen has a very short lifetime. So when it is formed in the atmosphere, it is quickly eaten up by other species and doesn't live very long in the atmosphere. So that's why you can see as you go up, every panel is an altitude slice. And as you go up, you see that the hydrogen cross-section kind of dials off and kind of gets smaller as you go up in altitude. But the H2 remains relatively constant and actually remains relatively stable as you go up in altitude. So that suggests that H2 actually has a very long lifetime. And dust storms actually contribute to the longevity of that H2 and actually helps it push upward into the exobase in the atmosphere and eventually escape to space. So dust storms, the extended water cross sections, and the latitudinal analysis of our work actually do prove that the near surface chemistry is actually highly impacted versus all of these analyses. And so in conclusion, The key takeaways here are we extended our cross sections to lambda is greater than 1950 angstroms. Again, previously 1D photochemical models actually stopped off about 1950 angstroms. So with the cross sections from Ranjan 2020 being greater than that, and they actually drop off about 2300 angstroms. And so again, CO decreases with extended water cross sections, nitric acid increases with extended water cross sections, and the dust storm analysis do show the mixing ratio of H2 formed as a result of the Hawk cycle does in fact decrease with altitude during a global dust storm on Mars. Sorry, actually, it actually remains relatively stable. And actually does decrease with altitude just because it's able to live that long to reach to the exit base of the atmosphere. So I want to say thank you to all of my co-authors. And here is my email. And here is just a picture of me if you want to reach out to me with any questions. I know we have to get to the networking section, but I'm always here for questions. And thank you so much.